If we have the label, then we know exactly to which obstacle in our world model it corresponds. So it solves the data association problem for us. Usually we would do that by, for example, comparing each state of an obstacle in our world model to a new measurement. But now you can just say, I recognize that this is robot number 4, opponent number 4, so hence we update the state of opponent number 4. And that mainly helps when robots are driving fast, accelerating fast, or very close together.
Or occlusions.
Or occlusions, yeah, if you only see part of a robot, but you do see the label behind. That helps.
Yeah, so conceptually you can use a distance criterion. So conceptually you can use a distance criterion, or for example, but yeah, now you have more confidence that, or you have more information that that robot belongs to the previous measurement.
Okay. Any other questions? Oh, yeah.
And now I see, of course, also the major complexity of this trick, because you need to be expecting that the label could be anywhere on the robot in any given position, with made on any given label, a material like reflectivity or color shades or whatever. So that makes it extremely complex to recognize those labels or not, because the label quality as such is not standardized. We just have to have a number in a certain color, that's it. And then you have massive variations on the theme. And that's extremely complex or not.
Oh, yeah, yeah, and the problem is the farther away the robot is, the less number of pixels you have to recognize it from the pin. So there are many variations. Did you understand what I said? Or should I repeat? So the farther away the robot is, the smaller the picture gets, so the less pixels you have to feed the network with. So, and currently my biggest problem is that the pictures I took are from labels with different colors than the ones we shot at the last time that we were having a competition in where we go tomorrow.
In the lot, yeah.
Yeah, and so I want to shoot some new pictures, but also have the tracking information from our robot so that the images are the same ones. Right now, the recognition, as you can see on that little thing on the left, all the variations are recognized almost perfectly, but the one on the right is from the omnidirectional camera, and it's very hard to recognize that and match it with the generated images. So that's what I'm working on to get that better.
There was a question here, I think, as well. Yeah?
That's related to the recognition. Do you also in your training set you have lighting conditions?
Yes. So in the program you can actually set a number of variations for each of these different parameters, so you can change the lighting conditions, and currently we have 16 different variations only on the lighting. But then you have the angle, the size, and the distortion.
Yeah. And also, but also let's say occlusions. Partially that number is only partially visible.
No, I've not included those. Just shearing and rotation and all kinds of distortions related to the distortion of the mirror of the omnidirectional camera. Those are the ones.
Being a hardware guy, I have to ask this question. Where does all this computational work take place during the game? It's on the robot, right?
Yeah, but in the GPU. Can only do that on the GPU.
Yeah. So will you add something, or will you just keep the stuff you have?
No, the Jetson boards, I hope, will be sufficient to do the execution part. The training part is the hard part. And I have a 1070 GPU on my notebook, and training of those 60,000 images takes about 1 minute with the current GPU. On the MacBook it took about half an hour.
And during the game, the OmniVision camera needs to pick up that number, it reads the number,
Yeah.
and then it needs to calculate on the spot which robot it is,
Yes. And it
with
is that
the train data.
for the entire image.
Yeah.
And we hope that with the networks that we're working on, that we can do that at a frequency of around 20 to 30 hertz.
Okay. Yeah.
That's only the inference, eh? So the inference stage, the network usually takes less time than the learning phase. And even if that would be a lower rate, let's say 10 hertz, that would mean that we would be able to detect labels with only 10 hertz. The obstacles are still being detected with 60 hertz update. So that means that every per 1/10 of a second, we get a label detection, and maybe also multiple detection, which we can easily associate. In between, we just keep the label and propagate the estimates of the object. So, in that sense, it will contribute to the robustness of the tracking. Still, even while we can only get a limited number of updates per second.
Okay, thank you.
Does that answer the question? Then there was one more here. I'll pick up the microphone here.
Yeah, very interesting, the 8-wheel configuration, and I think that gives the possibility to also use bigger wheels, and which would not limit you to these very perfect plain fields that we have at the moment. Of course, yeah, in real football games, you have to live with the circumstances you have, with long grass and bumps in the field and those kind of things. Is this also one of the thoughts behind this system, or how should I see this?
Exactly. Hardy came in exactly at the right moment. Is this one of the thoughts behind it? Nice question. Yeah, it's indeed, I can answer it. It's indeed possible. So we could use bigger wheels. At this moment, I think the radius is about the same as the Omni wheels we currently have. But as, of course, with the Omni wheels, you have these passive wheels and circumference. And yeah, there can be grass inside there. And that will hopefully reduce maintenance we need to perform on those wheels.
But also, you cannot move sideways because small wheels cannot go over the bigger.
Yeah, that's also, yeah, indeed, that's true. Yeah. Anything to add there, Hardy?
Only we had bought now units from 1.6 kilograms, and the wheel units now are 3.2 kilograms, but we want to increase decrease the weight of the platform, and also we have thought about the as we call it, over the path. I don't know, statically overdetermined. There is an X in the middle, so it's not, that's that one, yes?
Yeah, so it's not anymore statically overdetermined. We apply some suspension items there. Yeah, there was one more question over here. Yeah, I think room for one question because we also have the other teams.
Well, okay, maybe we defer then. So at the beginning of the presentation you were talking about improvements on the low-level motion control with implementing like a new cascaded control and some feed forward. Is there anyone who can make a comment on what's going to happen there? Because earlier I took the liberty to have a look at the current implementation of Tech United in the source code. Is somebody able to give a comment on that, or maybe refer me to the person that could do this at a later stage?
I think that if someone could do it for us here present, it would be Jannik, but Jannik is looking so confused.
I was texting, sorry.
So more elaboration on the low-level motion control improvements, cascaded control and application of foot forward.
Ah.
That is actually Dennis' part.
Yeah.
So yeah, you could contact Dennis for the exact details. You should contact Dennis.
Okay, will he be joining for this tournament or tomorrow maybe?
I don't think so.
Okay.
Maybe. Yeah, Fanny might also. No, and he's there on Saturday.
Okay.
I think.
Then we'll defer the question up till later.
Yeah. Because if you really want to get the details, I don't think we know the exact details.
Okay.
Yeah. So then I think we'll continue because also the other teams, of course, need time for their presentation. So then thank you from Tech United, and then we can continue to the next presentation. Yukiko, are you ready? Are you ready?
Yeah, how to use it.
Yeah, so it's just this button to go forward. Yeah, so this is forward and back. The laser is this one, so this. Yeah, maybe I will introduce you. Don't worry. Yeah, so the next presentation is of course a really special one because we have actually a visiting researcher here at our team, Tech United. This is Yukiko Matsuda. Right, yeah. Yukiko Matsuda, indeed, pronunciation-wise. And she's from Hibikino Musashi. She's visiting us and she'll tell a bit more about Hibikino because maybe most of you don't know the exact details about Hibikino Musashi. So Yukiko will tell you everything about it. And then she'll also tell something about the current status at Hibikino Musashi. So Yukiko, if you want to stand here, then also the fans in Japan can see you. Are you ready?
Yeah.
Good luck. I think can you talk?
Sorry. Hello, I'm Yukiko Matsuda. I'm from Hibikino Musashi of Japan. I talk about Hibikino Musashi team and ours robots. And so you know RoboCup. What is a RoboCup surplus? This is a landmark project. So the autonomous robots team win the human World Cup winning team by 2050. So this is final goal. And there are many leagues we are participate middle-sized league. So this is my team neighbor and ours robots. And Hibikino Musashi is a joint team of 4 universities. So I'm from Kyushu Institute of Technology and other universities the University of Kyushu, Nippon Bunri University, and Nishi Nippon Institute of Technology. And we are 9 times winner of the Japanese championship until last year. Now we want to be world champion of RoboCup World Cup. So I have a question for you. Where is the Hibikino Musashi place? Please find the Fukuoka. And number 1, 2, 3, 4, 5.
That's such 5, I say 5.
Okay.
No?
5? Really? Other 2? 2? 1? 1? Okay, let's answer together. So number 1 is Hokkaido. It's not the Fukuoka. So there are now it's so cold, but sushi and sashimi is very, very good. But I have never gone here. And next, number 2 is Tokyo. Tokyo is a capital city. And number 3 is Aichi. Aichi has had much Robo Cup, so we joined the Robo Cup together. And next, number 4 is
Kyoto.
I know Kyoto. Yes, this is famous tour place. So last number 5 is correct. This is Fukuoka, our working displays. Yes. So what is Hibiki no Musa's name? So Hibiki no is place name. This is Fukuoka, and Hibiki no is this area. And so Hibiki no's name from Hibiki no place. And Musas is a famous samurai in Japan. So he is Musashi, Miyamoto Musashi. So we take his name. And this one, our university. Okay. So I talk about Hibiki no Musashi's robots. And they have 4 mechanisms. Omni camera and omni wheels, kicker, and driver. And omni camera, they can watch 360 degrees with a camera and omni mirrors. Next, omni wheels. They have 3 omni wheels and with the encoder. So they can move front and back and left, right, and they can turning. Next is a kick mechanism. So we use the solenoid, so using the electric, so they can kick the ball. This is 2 types kick. They can ground and root kick. And how to say? This mechanism, this can move the down and up, so they can kick the ground and the roof. And the last is driver mechanism. So they have a small wheel, so they can move the ball and kick the ball. So they can move turning the keep the ball. And our task, we have a lot of tasks. This from World Cup from Nagoya. And so we have many tasks: software, hardware, electronic circuit. We divided the main task. So I challenged to this electronic circuit. I can make the electric circuit and sensing board. So my major is electronics. So, and we challenged that there are many tasks. We challenge many tasks. After we tried moment band humanoid circle strategy on the robot. This is our challenge task. And also I challenged this my major communicate information between robots without Wi-Fi using the arc marker and the range clearance image. Range clearance is this image can show the different image one markers. So I want to use this, and I want to detect the degree robot's angle. So if can I use the markers, maybe they can pass and positioning without Wi-Fi. So now I study hard. Yeah. So this is it. So thank you for listening.
So I think we'll have time for one question for Yukiko. Any questions for Yukino Musashi? Yeah. EDL was first.
Who is that?
Yeah.
Excellent. You told about your role, so you did electric, and how many people are in your team, and do you have also divisions between one person does this, one does something else? Your divisions in the team? The role of your people.
We are we are the team members, and yeah, like I'm less than 15 members, and I'm only electric major. So they are hard or software making.
Does that answer the question? Yeah. Well, then I think I have. Can I have the microphone for a moment?
Is that true?
Yeah. Yeah. Okay. Okay.
Yeah, because we are very glad that Yukiko came to us and stayed for 2 months in our lab. So we want to thank her with a little present and also with a big round of applause, of course, Yukiko. Thank you very much.
Yeah. So I think after you've unpacked your presents, she'll unfortunately be leaving this Sunday to Amsterdam, and then she'll be flying back to Japan again. So we hope you have a nice time there.
Yes.
Back, and then good luck.
Yeah. Thank you very much.
So then I think we're having the presentation of Nubot next. And yeah. Yeah. Go ahead. Let's see what. Go ahead. This is the pointer. Okay. And the laser pointer is the red. Okay. Okay. That's right.
Good afternoon, everyone. I'm Weijia from Newport. Now I'm a first-year PhD student in the University of Groningen. So so it is a great chance for me to come here to present some work of our team. So my presentation is mainly two parts. The first one is our robot, and the second one is about the simulator. For the robots, we introduced something that actually have already introduced in Japan, but just for for people who have not attended the competition, we will introduce again. And then the simulator, we introduce our simulator and also some thought. I think all of the teams use the omnidirectional camera for the vision, but there are also some drawbacks. For example, as the distance increases, the error of the object recognition detection is increases, and also it's very difficult to get a 3D position of the soccer ball. For example, if the ball is bouncing, so there are so large errors when you want to get a position of the robot. So actually, it's good to have a Kinect to assist the object detection for the omnidirectional camera. So, but you know, if we want to process the information from the omnidirectional camera and also Kinect, you consume so much resources. So we try to use TX1 here, and we also use the ROS framework. So the TX1 is processing the data coming from the Kinect, and it uses the CUDA parallel computing based on using the GPU. And then after this process, you transmit the data using the ROS messages to the industrial computer. So actually, the ROS master is in the ROS industrial computer, and they are connected using a wire cable. So actually, the communication middleware is very easy because it is based on ROS. So just transmit the ROS messages. Okay, so this is the very simple architecture of this structure. So the industrial computer uses the CPU to process other modules, and the TX1 uses the GPU to process the data from the Kinect. So there is high accuracy, and it is able to obtain the 3D position of the soccer ball. Because this year for the technical challenge, although we did not perform very well during the technical challenge, but actually before the game, we are quite successful in performing all the skills for the technical challenge. One thing is that the robot has to kick the ball into the air, and another robot should catch the ball. So we should obtain the 3D information of the ball so that the other robots can catch it accurately. So it is very important. And for the third one is to detect arbitrary color obstacles. So you can use Kinect. You can use the depth information to determine an obstacle. So we don't just depend on the color information. So this also in the technical challenge. But there is a drawback. if we just use the Kinect, because the vision range is limited, so we are considering how to let the robots, like 5 robots. So we are going to figure out they should cooperate so that they will get the best region of vision, best coverage of the soccer field. So different from the past, because in most cases we try to let the robots look toward the soccer ball, but if we only use the Kinect, we can only have a very limited vision range. So if you can try to let different robots heading towards different positions, different directions, so that maybe we can get the optimized coverage of the whole field or just some regions that we're interested in. The second subsection is that we try to use the machine learning in our robots. So we try to implement YOLO framework. It is a unified real-time object detection framework. It is based on the convolutionary network, because we think machine learning will be very important in the future development of the robot soccer, because we just if we want to develop it better, we should let it learn autonomously. So the first step, we try to use this machine learning to distinguish robots from other obstacles. So this is the preliminary result. So actually we also have a data set for the middle-sized league robot. It is in our GitHub. So if you are interested in, you can access this GitHub and get the data set. So there are also some problems. The first one is the real-time requirement are not satisfied yet, because you still have to consume much time for the learning and the recognition. Actually, we have already done some optimization. We use the CUDA parallel computing to try to increase some computation time, but it's not enough. And the second problem is the precision. So we are going to work on that. So there are some 3 possible future directions. First one is because the training data, the training image is from a camera, from a normal camera. So I think it's better to obtain the image from the Kinect, because it is different from using a normal camera. And the second one is try to simplify the neural network architecture so that we can increase the speed. And the third one is trying to combine the depth information to train the network. Maybe we will get better results. Okay, so the 3 subsection is our goalkeeper. We designed a new goalkeeper in this year's Japan Championship competition. So we use 2 Kinect sensors here, and we have a framework which can extend it so that to stop the ball from coming to goal. We use the gears guide rail for this. Okay. So the second part is the simulator. So actually I introduced it before. So and I try to emphasize here. I call this simulator the growth sim. Actually, this name is I just give it a name like last night. I think maybe it's a good name because it is based on ROS and gazebo. So I use the G for gazebo and ROS for ROS. So it's a growth sim. So it's a very simple name. So yeah, you can actually I have done a lot of documentation in GitHub, so if you are interested, you can try to use this simulator. It is a 3D simulation, so I'm going to introduce some advantages. The first one is this simulator is very easy to be adapted to different teams. So you can see here is a very simple structure of the code. So the green one is the gazebo models. So this model is actually like a real robot. It can, if you send a velocity command to it, the model can move, and you can also publish the wall information. And if you like call the ROS service, it can shoot or dribble the ball. So the interface is the ROS messages and services. So you can see here, the first column is the 4 ROS messages or service that we use as an interface. So you don't have to care about how the robot model is, or how it works. You only have to send these ROS messages to the robot, and it can do all the required motions. And you can also obtain the wall model information just using the ROS message of the vision info. So we have already used this simulator to do some research.
Bringing good here.
Also the first video.
Oh.
So in most of the research, so in this research you can see the soccer ball as an enemy. So it's an enemy that we try to enclose the robot and enclose the target and entrap it from escaping. So you can see that the spacing between each robot is changing. So it try to simulate the situations when different robots have different kinematic abilities. So some robots may move slower than others. So we try to decrease the spacing between 2 robots so that they can compensate for some efficiencies in their kinematic abilities. Okay, yeah, and also if, for example, if a robot is broken, so you move. In this case, I'll just let the robot move away, and it can adapt to this situation when there is robot quitting or joining into the formation. So actually, I did this experiment first in the simulation, and I did not modify too much, and then I can implement it on the real robot. So it's very convenient for me. And the second one is for the communication is ball passing. So it is also in the technical challenge. This is based on the incomplete information game theory. So we design a very simple GUI to do some experiment on this. So each robot cannot communicate in using Wi-Fi or something else. So they just so it's like based on the game theory. We try to do some research on this. Okay, so the second advantage is it can simulate gameplay and replay. So can you start the video? Yeah. So this one is the the China Robot Competition Middle-Size Simulation League in last year. So it is a competition between newborns and a team from Central South University in China. So you can see they are actually competing against each other, but yeah, but it is not very perfect now. And you can see here in the top left corner is the referee. So it judges whether the robot violates the rules or not, whether you have a goal or whether the ball goes out of the field or not. So it's very simple, like command line interface. So we are trying to make it as a GUI, so it is better looking. We also use the raw spec to record all the messages during the game, so we can replay all this information, all this data. And also, so we are trying to increase the robots in the simulation. So in these two videos, we try to. Is it working? In these two videos, we in one single laptop, and we try to let 12 to 15 robots running in the single simulation. No?
No. Shall I show them?
Try again.
The videos.
Okay. Yeah.
Which one is it?
Whatever.
Whatever.
So here there are actually 15 robots, and we can see the red robot as the target. Also, we try to encircle this robot. And maybe you can try another video.
Yeah. Let's see.
Yeah, so here I think it's like 15 or 12 robots. Actually, it runs smoothly in one single computer, but when I use the screen recorder, it is not that smooth. So can I go back to the site?
Yeah, sure. Let's see, it was. There you go.
Yeah. Okay. So actually, we can distribute the computation in several computers so that maybe more and more robots can join in the one single simulation. Actually, in the China Robot Competition, we use 3 computers, and one of them is used for the server, and the other 2 is for the client. So these three computers communicate using a wire cable, and it is able to, I think, it's like simulate more and more robots. So the fourth thing is why we use 3D simulation. So actually, Happy Northern Castle has mentioned about this 3D simulation. So we are able to simulate the ball kicking into the air, and I also thinking about another a possible future direction. So now we use the goalkeeper only has to obtain the ball information in one direction. So we can goalkeeper can move to this side to block the soccer ball. But I think it will be more challenging if we have a robotic arm on the goalkeeper. So the goalkeeper has to know exactly the 3D position of the soccer ball, so we can move his robotic arm to stop the robot. So I think it's more challenging, and there are more research directions in this. Okay, the fifth point is This software is open source and it has detailed documentation. You can see actually there is some Chinese, but most of them are English, so I think most people can understand it. So actually, I also welcome you to contribute to this repository, so because it is not perfect, it has a lot of things to work on. So you can, if you are interested in, you can access our Newport's GitHub repository. So for the cross-platform, I read the slides about the simulator. I think it's from the video spot. I'm not sure. So it is okay. Yeah. So it mentioned about that they try to use a mobile phone to.
Just as an ID, not that we're currently working on that.
Okay. Okay.
But the ID was to give the agent a specific character, and not have 5 agents the same, but and
okay.
take it with you.
Okay.
And the mobile phone is sort of a metaphor for that ID.
Okay. I see.
Yeah.
So yeah, actually, I think one of the problems is the cross-platform, right? So, for example, you have an Android system or the Windows system. So, how they can communicate and different teams, how they can cooperate in the same simulation. So, I think one possibility is to use the web page, because whatever you are Android or Windows or Ubuntu, you have a browser. So our system has a browser, so you can use the web page as the interface. So actually, ROS has already something related to this. So it's called the ROS bridge. The ROS bridge is able to use, so it provides a JSON interface to ROS, so that non-ROS programmers and non-ROS platform can access and use ROS. So if we combine this with our simulator, like the Golf sim, so maybe we can just, the cross-platform can be solved. So maybe in the future we can, you only have to provide some post messages or some JSON messages. So I think all the teams can play in the simulator. So okay, thank you very much.
Yeah, thank you. So, any questions for Joseph?
Actually, it's not a question, but it happens that a week ago I made a Docker file for installing your simulator.
Okay.
So if you want to have access to it, it's on GitHub.
So, what do you mean? Sorry.
Yeah. I've created a Docker file.
Yeah.
You know the Docker technology?
Oh, yeah, I see. Docker, yeah.
Yeah, so I Dockerized your simulator for use because
oh, great.
so that you can easily install this stuff.
Yeah, that's great. So maybe you can send me the link and I can post it on my GitHub. Yeah, thank you for your contribution.
Any other questions, remarks, suggestions?
So you mentioned you wanted to work with Kinect and you wanted to map your soccer field with several Kinect cameras, right?
Yes, right.
Yeah, okay. So the thing that crossed my mind is you have these Kinects on your robots and you want to position them in such a way that the whole field is visible. But isn't it much more preferable to position your robots according to game strategy roles instead of trying to map the field with them? Because those two things might clash, right? A good strategy position might not be a good position to map the field in. So what takes priority? Have you thought of that? Or?
No, I have not thinking about it. So yeah, I think it's a good idea. So you have a balance between these two. Yeah. So I will think about it.
Okay,
thank you.
Any other questions, remarks, suggestions? No further questions, remarks for Nibel? No? Okay, then we thank Wijja from Liverpool. And then it's time for the next 15-minute break. So enjoy the coffee and tea.
Ja, dat kan. Ja, dat bedoel ik. Je moet ook zelf naar weer met de rest naar de diner. Ik loop al een beetje uit. Ik had niet altijd wel tijd tussen het diner en de laatste vergadering. Oké, maar kunnen we eventueel yoghurt en die samen... Kijk, kijk, Jan.
Doe jij dan, wij ruimen hier alles op, kun jij dan de spullen meenemen? Ja,
Pas de probleem.
Pas de probleem?
Pas de probleem.
Ja, hè? Voor jouw preventielijst. Je had het altijd mensen die dag niet, hè?
Ja, opletten dan.
Ja, dan buiten geen extra.
Ja, precies. Ja, maar dat is goed. Dan zal ik je daar weer.
fouten ben ik heel vervelend, want ik zeg ik toch graag mee eten. Oh, nee, dat is geen probleem. Dat is geen probleem, dat komt echt goed uit. Want 9 uur, half 10 thuis, dan rijden we goed aan. Ja, dan rijden we gewoon. Ja, nee, dat is goed. Oké. Goed. Even checken. Even nog distribueren. Kilo bij. Je moet echt op. Ik wil dat even mee terug. Looks like kilo, so they're more because you're only human walking the place. So they're not equal like yeah, other teams. There are other teams and how much or how many teams there? Wat kijk ik zelf? Is moeilijk. Ja.
Gewoon hier, het volgende automatisch.
Geen apps. Oké.
En als hij uitvalt, dan moet je gewoon op daar klikken.
Gewoon stream. Ja.
Ja,
En waar zie ik dat die uitvalt?
Ja, of je krijgt een grote melding.
Ik heb een linkermaat.
Slides omwisselen.
Even kijken.
Een slideje verzetten. Ik had al 2 gewisseld.
Ah.
Dus de team update slide was, ik had hem gedupliceerd voor het begin, maar die waren gewisseld met elkaar. Jammer dan. Maar die is goed. Oké.
They're like these, only better. Yeah, 3 different flavors. They're these. Do you know them? Yeah.
Oh, heerlijk.
Even kijken, dit is denk ik een makkelijkste microfoon.
Ja, de microfoon was nou.
Ja. Ik heb het bij als een ja. Ja. Dus ik was eigenlijk lijkt dat het een buitje.
Ja, daar heb ik
So, if everybody's ready, we can start again with the next presentation. Everybody got a handful of papernoten. Papernoten? Yeah. Peppernuts. Indeed. Then we can continue with the presentation of video robot sports. So, Tom, the floor is yours.
So good afternoon, my name is Tom Pijnenburg. I'm team captain for Robot Sports team. I'd like to give you an update on where we are. I apologize for being late to the meeting, but I had to miss the first few for giving another presentation on a very different topic, by the way. What is Robot Sports? It is a team driven by people who do not work at universities, they work at professional companies, and they are captured by the idea of autonomous robotics, and they like to work on this. And for most people, this has a relation to their day-to-day job. It's not a very direct relation because robotic soccer players are not being made commercially and sold commercially, but derived technologies like autonomous navigation in warehouses or container terminals actually is a product right now. So certain people are interested to learn more. There's other people that like to learn more about omnivision processing, whereas they normally do mechanical engineering. So there's various profiles of people we have in the team. We have a 1 day a week hobby evening, Wednesday. We share the facility with the ASML Falcons. So ASML was so friendly to prepare the facility, and now we share the burden of the monthly rent. But that's okay. I think the preparation we still haven't paid back in rent, right? That's more of a cost. So it's all alone. Actually, we go back to certain people in the team. I think about half go back to a team in Philips, Center for Industrial Technology, which we then called Cyber Football Team, and we started participating in 2002 in the RoboCup Mid-Size League. We'll come back to that later. So if we look at activities at the moment, the actual ongoing activities and also the ones we have planned. So we're improving the keeper. We're not up to the level that, let's say, the best-in-class keepers are, but we're adding Kinect sensors. We found out that we need a second one to look at the balls that come flying at us, especially after Falcons practiced a lob shot. So now every practice match we do is a 10-0 or something like that. And if we're successful, it's 10-1 or 10-2. So we needed a mechanism on that, and we need to have input to operate that mechanism, and that's something we're working on right now. And actually, he's the youngest member in our team. He's a guy from 17, still at middle school, getting ready for university, and spending his time on that topic. We're improving our OmniVision sensor. Like everybody, it's a crucial sensor, and it's limited in its performance. I think we have the widest view in the mid-size league in terms of we are able to see everything, but it doesn't mean we're the best in drawing conclusions from the sensor. And that's, let's say, sort of a headache for us. So we try to improve. One of the things is auto-calibration. What if most of the pixels are field? Then you know what color is, right? Why do all this tedious color calibration stuff? We're still busy with that. Speed is an issue. We like to move. We're currently at the 20 frames per second for an HD picture size. We want to move up. And one of the directions we chose is not so much in the GPU, but more in the automotive. In automotive, there's a whole class of processors, system on chip, SOCs, Freescale, S32V, and they also have an S32R, and the V is for vision and the R is for radar. And those are processors for automotive applications, and the V is capable of processing 2 HD cameras simultaneously. And it has 2 stacks of 64 cores, and then another quad core and GPU and something else, all within a power envelope of 10 watts. And that's impressive, and I think that's relevant for our competition. I used to think that the innovations that we use in terms of technology, putting on the robots, comes from consumer electronics, smartphones. Now it is driven by automotive. And there's a very big push there, and we should, let's say, create some hooks onto that. So VDL is active in automotive. We make buses, and we will be trying to make them autonomously, drive autonomously. We make AGVs for container terminals, but I think there will be a convergence of these fields. So I think it's relevant to look into these kind of devices, and not specifically start with the, but that's our direction. And another way to improve it is to get rid of it altogether. I think if you look at trucks that now create vision around the truck for safety by just using webcams, there's other ways to get information. And maybe that's the direction we want to go. An important thing for us, since sometime we have are able to pass balls between players, and we see that it's imperfect, and it's imperfect for a number of reasons. The main driver is the inaccuracy of our positioning in terms of the world model information, but the second factor is the inaccuracy of the mechanism, and that's something we need to work on. So it's a hardware-software related topic. One of the directions we think, and one of the guys now starting to work, but starting up slowly, is to apply machine learning techniques to improve this shooting between the robots. We know when a shot is made good, the robot receiving knows when he has the ball, and if that's within the planned time, it might be a successful pass. So we can use that as a learning input. An important issue that's bugging us right now is the wear out of our hardware. Since we started, I think 4 years ago, we haven't made any changes to the hardware, only slight upgrades. That means that parts now start wearing out. And that's something that we attend to. It's costing us money, so that's another factor. So that's hardware. If we look at software and controls, team play is the focus for us. It's been in other presentations as well. So positioning well and executing a pass and executing a set play. So we looked it up a little bit before you did, I think. But we're struggling with the same things, and then at some point in time we found out that there is even a name for it, so we call it set play. That's something we've been looking into. There's more information on that. For us, the struggle right now, one of the main struggles is to get the correct information in the world model. And we still have lots of noise and lots of uncertainty on the observations, systematic and stochastic or chaotic. I think most of the noise we deal with is chaotic. And that's one of the inputs I think for the simulator workshop. If we have a simulator that simulates Gaussian noise on sensors, it's not something we cannot develop a control for that and expect it to work in our robot. Our robot does not face Gaussian noise. Our robot faces chaotic noise. Sensors go on and off, and they are out for 4 frames, and they are back, and they have a systematic error of 1 meter, and then they get a new update, and then the error is 0.1. It's very different from Gaussian, and I think that's why previous attempts in the leagues to convert from simulation league to mid-size league have not been successful in that extent. So that's one of the interesting things for me for this workshop. And yeah, decision making, which roles, which positions, which tasks. Come to that. Grand challenge. I think there's one grand challenge, and that is to scale the. Can we scale the learning of our agents? And by playing a soccer match every now and then is not enough. And I think it was said before a number of times. That's the big motivation, I think, to think about learning in a simulated environment. There's an industrial relevant context to that. I think if you build big machines, then there is a significant aspect of that functionality of the machine which is implemented in software. And teams building big machines, and whether it's a production machine or a car, are not capable of testing and developing all that software with the hardware present. They have to develop it in a virtualized environment. And in this virtual environment, the single aspect that's relevant is how representative is my model for something that will happen in the real world. So that's, I think, a very important topic. So this is about where we are with our robots. So we're end of warranty, according to this slide. Cooperative team play. This is the structure we have in our control software. So we have a 40 Hertz update in that system. It doesn't reflect right on the screen. Okay, we run a 40 Hertz loop here. And every 40 Hertz we process our sensors, we update our world model, and we update our tactics. If you look at this behavior, this is what it's about. We have implemented that in a programmable state machine. So we have skills, and we have decision skills. Skills is an action, and the decision is some sort of a sensor reading. And we can combine that in a script, and that script describes the behavior. And depending on the situation, we can change scripts, and the script is equivalent to a role of a player. So that kind of system we have. If you look at the previous tournaments, and we did not participate in Japan, but we did participate in Portugal. And then the issues you saw with our robots was multi-robots trying to capture the ball, do not capture the ball from our own players, and these kind of things. But very fundamental, elementary issues almost that go back to this inaccuracy in world modeling, and the fact that based on that incomplete or incorrect information we make the wrong decisions. Here it is again. So the tactics we run at 40 Hertz. Our team planner is updated at 4 Hertz. So the team planner decides which are the best positions from a position play point of view. And the tactics decide for each robot what will be the action in the next moment. So we have a flow, game state, and from the game state we decide do we have the ball or not. And based on that we have fan out in opportunities options that we select from based on various criteria. So these are the roles we see. Well, that's not something new, I think. What was new for us, and that's relatively recent, is that we have set play kickers and receivers. So we have a coordination when we do a set play, like free kick or something like that. There is a kicker and a receiver. And the receiver signals to the kicker that he's ready, and only then the kicker will shoot the ball. And that's also for us a limiting factor at the moment because it slows down. Because in some cases the receiver is not in position, and only then will be a signal that he's ready. And then you see something that looks like a robot is stuck, but it's not. It's waiting for the signal to be ready, right? So here we need some more robust strategies in terms of dealing with this. Toolkit as is. I think we should leave it like that. This is too much detail for him. One other topic I'd like to discuss. I previously discussed with Lotte briefly, and with more wheels, we think less wheels. So let's see. This is our robot in 2001. We're still in the mechanical workshop of Philips. We did not have the smart decision to put two powerful motors. We had one powerful motor for powering the wheel and one less powerful motor for orienting the wheel. So this is a mechanism that was also somewhat comes back in the 8-wheel robot that Tech United is now proposing. So quasi-holonomic, it's not real holonomic. This has singular states, and because you have to control 8 degrees of freedom for moving a robot and 3 degrees of freedom, we decided in the end it was cumbersome from a control perspective. That's why when we restarted the team in 2013, we decided to go for the 3-wheel concept. This obvious has more traction, so we know. And our robot was quite heavy, it had old technology, big boards and big batteries, still nickel cadmium batteries at the time. So we decided to move away from it. So it's interesting to see how the arguments play out. I'm looking forward to discussions on that. So the 4 wheels, 8 degree of freedom control that you need for the 3 degrees in the field. There's singularities in our mechanism that we had at the time, and the cost. So more motors, more amplifiers, more everything. So why do we think less is better? The clearance. Our robot, but it's not the principal aspect of 4 wheels or 8 wheels. Our robot and the current omnidirectional robots are designed for low clearance. They play on a billiard, table billiard kind of surface. If you move to an artificial grass surface, it's more complicated. The traction is not good, so you need higher clearance. And higher clearance in these concepts, and when you have many wheels, it becomes a complicated concept, especially in the form factor. On the other hand, there is proven mobility with a 2-wheel. And the thing that struck me, and I'm not sure whether the movie is running, it's a YouTube thingy. Do we need to press it?
Yeah, I can check it.
Maybe.
Yeah, I'm not connected to the internet.
Okay,
no.
Then it doesn't work. We should have downloaded it. This is a movie of Segway robots that are used by the Pittsburgh Steelers. This is an American football team. For training the defense. And training the defense is about training tackling. And tackling in American football is not a body-friendly activity. So what they do is a Segway with a remote control, and they put some foam on it, and it looks like a player. And they run it around. The coach controls it. It's a remote control. And then the defenders try to tackle it. That tells me what, and it's called mobile virtual player, not the most valuable player, but mobile virtual player. It's a company, startup company, selling them to teams right now. And that tells me that you can run on a real surface for playing soccer or American football. They're equal surfaces, and they have the speed. And then what we did next was have one of the box boards, the hoverboards, and give it to my kids. And we don't have a big house, so I see the maneuvering, and I think the maneuverability is also okay. So all the ingredients together, I think that for $200 each, you can have a motion platform which may be suitable. The thing is, in 2006, RoboCup had a Segway competition. It was driven by Manuela Veloso in the car from Carnegie Mellon, but it was only 1 year. So now either of two things is true. Either the concept did not really work, and they decided just to abandon it, or the group of Manuela ran into the fact that to operate a Segway platform, you need also to have hardware competence. And I think that's a little bit more what the MSL is about, mid-size league, hardware competence in combination with the artificial intelligence. So I'm still in doubt. I didn't get an answer from Manuela on my emails, so maybe you, what do you think, René?
Normally she answers. So
yeah, so it must be a very bad question. Well, she will not recognize me. Yeah. But I think there's also, in addition to these clear advantages, there's the advantage in cost. And let's say, hoverboards are everywhere. They are made in China, mostly, all of them, I think. And they don't suffer from the fact that if you buy them locally, you have to be careful about the batteries and shipping batteries, which is also going to be a limiting factor for us. I'm not sure how that develops moving forward. So we are looking into a two-wheel platform as a cost-effective alternative. So if anyone has ideas about why this would not work, and there's many, for instance, if you move a two-wheel robot against the wall, it's stuck. It cannot move back because it needs to tilt in the direction of the wall to start moving. So how does that work? So we're welcoming feedback on that idea. Yep.
So, any questions for video robots?
Probably you've already thought about it, but what happens if a robot on two wheels is hit by another robot? It falls down and cannot stand up anymore, or?
Yeah, yeah. So we thought about that. So you need to have some mechanism to recover from that. And when you look at the MVP, the mobile virtual players, they have additional wheels, and there's sort of a tumbler that you put with the baby, right, for playing it. It's a self-righting mechanism that they use for that. So I think there is a number of strategies that you can use to get upright again.
Yeah, so probably this extra wheel could also be used to just go away from the wall, something like that.
Yeah, yeah, yeah.
Any other questions? Yeah.
So you mentioned high maneuverability for a two-wheel platform, right?
Yeah.
But isn't that only in the rotational situation? So if you're standing still and you want to accelerate, then you need to tilt first, and then you can start accelerating.
Yeah.
Which means that you're slower than a platform that could have started accelerating right away.
Yeah, that's true.
So
theoretically, it's a slower platform. I think that's why many decisions are that you don't want to use it. If I see how my kids operate on a hoverboard, they are able to create the dynamics that I think we do not yet see with our robots. Even though we have high accelerations and immediate torque and these kind of things in omnidirectional, still I think it's a matter of how effective do you bring your intention into motion. And it has something to do with the capability of your motion platform, but it has also something to do with the higher level skills that you need also to develop to defeat the world champion in the end.
That your kids are continuously moving their bodies, so that's not just controlling the wheels, right? That's a moving mass on top of these wheels.
Yeah.
That's why it's maneuverable for people standing on a hoverboard like that.
Yeah.
So you're planning to do something like that?
Yeah. Well, the first test we did was to have a weight on the hoverboard and control it with a servo and drive rounds on our field, right? With a servo, but the servo was just controlling the wheel the servo was just controlling the mass on the hoverboard. And that's you apply a center of gravity mass to the robot, and then it starts doing things that it's trained to do. You can also hack into the hardware, but the elegant thing is to bring your own system and click it onto a hoverboard and start playing soccer. That was the idea. But yeah, and I'm not, I don't have all the evidence ready that it will work, but it's too compelling not to look into it.
So your test, how high was the platform?
Within the height factor that we need.
Yeah, so it fitted within the size limitation.
Yeah. But to be honest, we could not fit the omnidirectional camera on top again. So yeah, but it's not human height. It was MSL robot height. Yeah.
Other questions, remarks, suggestions? Lotte?
I had a question about the place the set place you were talking about.
Yep.
Because I've also looked into it for our team, and I remember when we were implementing, we were struggling with where are we going to make the decision to stop a play, for example, and to have to select a new one. So how do you, where in the software do you do that, on what level?
At the moment we have, and yours you need to correct me, well, we have a set play with 2 players. There's a receiver and a kicker. Once the receiver has received the ball, the set play is done. We're in game play situation again, play state.
That's a default game.
Yeah, but if it doesn't receive the ball, it's waiting on a timeout. And that's notorious to look at that because the player is sitting there and the Falcons take the ball and make a goal. So we don't want that.
We do want
so it's a hard problem, and we have a number of ideas on that, and we still haven't unified our position on that. Yeah?
Can I contribute to that?
Yeah.
So I'm not the main T-play guy, but I know that we had a discussion as well. So we actually didn't do the handshake, we set it as an intention.
Yeah.
So the robot that's actually gonna shoot broadcasts the intention, and the receiving part should then be aware of the intention.
Yeah.
But it will not wait before the actual handshake will be taking place, because then you're always too late in the game.
Yeah.
I think you need to swap the tendency there.
Yeah. That's one of the competing alternatives we have on the radar. Yeah.
At this moment, we only use the set plays to restart the game, and not in other situations, because it would be, in theory, it would be possible to also do it halfway when you're playing. We could initiate a set play at that moment, but we don't do that. So maybe the question that I got there was, when do you do this set play? So we only do it at the restart.
Other questions? Time for one more?
I have a question about machine learning for passing, how you envision this, because okay, you have your output variable that you can use as a cost function, be it the pass being successful or not.
Yep.
But for learning you also need some kind of input to the system or module that you want to train. So what are the inputs then of your system?
The input, sorry.
And how do you think about converging to an optimal solution?
So the convergence aspect is something of the machine learning strategy. The inputs I see is the kick power that we have, kick elevation, and we can add offset to the kick. So if we currently do the synchronization on the set play, so the set play receiver says I'm here, and then the kicker says okay, you think you're there, but I see you're a slightly different position. So we get rid of the error that is introduced by the set play receiver. So we take an observation of the set play kicker, but now the set play kicker position is off, so he's aiming wrong. So that angle is one of the inputs. Well, the other input is the kick power. So the harder we kick, the more narrow our error becomes. The softer we kick, the wider our spread is. But if you kick hard, you need to aim well, because otherwise you go past. So there is a number of 2 or 3 parameters that I think are input for such a learning strategy. And the output obviously is something that the receiver says within the allotted time, I have the ball and I control it, or you have an external observer that does say that.
Okay. And then the follow-up question would then be, do you have a model for this, or are you going to train this in real life?
Train in real life.
Okay.
Yeah, but it may not be the best approach. But that's the approach we take, or we propose at the moment.
Okay, then I think in view of time we thank VDL Robot Sports once again. Okay then, Ricardo, the stage is yours.
Okay, thank you, Walter. My name is Ricardo, and I'm going to present here the Kamada team. Hello? Thank you. I'm going to present the Kamada team presentation on this workshop. It's focused on our communication middleware called the real-time database. I have a small disclaimer to make before I proceed. This work is a master thesis work made by our student Diogo Silva, which is not able to be present, so I'm presenting the work for him. And this is the outline of the presentation. I'll start with a small introduction. I'll present very briefly our real-time database, the motivations and objectives for this work, and then I'll move on to the architecture of the new real-time database, some design choices that we had to make in the process, show you the new API, and also some considerations about back compatibility with the previous version. And I'll conclude with the results, conclusions, and future work. So let's start with the introduction. Our RTDB is an open source module that handles all the inter-process communication inside each robot, and also the inter-robot communication. It allows replication of the data among different agents inside the team, in a key value fashion, and any agent can retrieve information about any other agent at any time. And this slide will serve to show you how it works. So let's ignore the communications, the Wi-Fi communications for now. If you look at each agent as a robot, for example, each robot has local items and shared items. The local items are items that any process running on that robot can write to and read from. And then you have shared items for that agent as well. There's another process running on the robot called COM, which is very linked to the RTDB. And what this process is doing is broadcasting the shared items to all agents on the team. So what happens is that there's a COM running on agent 0, broadcasting its information, and then it's replicated to every other agent. The advantage of this is that if you are agent 2 and you need information from agent 0, you just read the latest one that you have available. You don't ask for it on the fly. So the API is very simple. You have an initialization function, a function to free up all resources, and then you have two major functions. You have one to write to the RTDB, and you have one to get information from the RTDB and from an agent that you want. What are the current limitations of the RTDB version 1? Basically, it's a simple binary storage of the data structures that we are using, and this is not able to store dynamic items, for example, dynamic arrays. And we wanted to be able to do that because, for example, one information that we share is the number of obstacles that we see, and the number of obstacles is dynamic. Sometimes we see 0 obstacles, sometimes we see 20. And what we have to do is to define a maximum value that we want to share. For example, 20, which is actually what we are using. And even if we only see 10, we have to broadcast the 20 because it's a fixed size of the structure. Also, the configuration scheme is static. You have to define it previously, and you can't put any items that the RTDB doesn't know beforehand. We want to be able to dynamically create items on the fly. Sometimes it's unreliable when agents are using different structures. So when the sizes of the structures differ, sometimes you have a warning and it just discards the packets, other times it just crashes. It's undefined behavior. And there's no compression on broadcast. We simply send the binary data over the network. So what are the requirements for an evolution of this RTDB? We want to maintain this blackboard logic so that we don't have to ask for the particular item for another agent. But we want to allow to have dynamic structures like dynamic arrays, like the std vector in C++ and the like. We want to have a dynamic configuration scheme to be able to add items on the fly by code and not have to define them previously. We want also to have changes to the structures resilient enough so that structures that come with new items, maybe let's discard those new attributes that we don't know. I'm an agent, I'm an older agent, and I don't know this new attribute, so I'm just focusing on the attributes that I already know, and I will use them, and just discard the new ones. And also the other way around, when we lack attributes when we receive, then just use a default value for them. Also, the need to recompile the code every time, because this configuration scheme will generate an error file that was included on our code, and each time we change the scheme, we write to that header file, which means we have to recompile the code. And time is precious during competitions, as you know, and we want to avoid it. And also a smooth integration with the previous RTDB value. We wanted to make sure that we wanted to test this on the competition, but also making sure that at any time, if there was a problem, we could revert to the previous version without any trouble. And of course, we want all of this, but we have real-time systems, so we want to make sure that we can do this in a very short period of time. So I present you the second version of the RTDB. What we basically want to do is store these raw data structures on some storage. This has the problems that I already told you. This is not tailored for dynamic structures if you want to store it directly in binary, and also not resilient to differences in data structures between processes or robots. So what we need is something in the middle that will serialize the data and not only store the values, but also store some metadata about those values, what those values mean. And then we need to send it through COM to the other agents. The problem is that this serialized data is higher in size is bigger in size than the raw data structure, and probably we will hit a bandwidth limit problem. So we need to compress it before sending. I will start by focusing on the storage. We used the key value storage framework, so we evaluated many that were available. The requirements were that it was free, it was non-copyleft license, it was an active project with in-memory storage and support for multiprocess and multi-thread, and because we were using C++, that would have a C++ API. So if you look at the market, you have plenty of options, and then you start discarding. For example, C3 is a commercial product. These two don't have in-memory capabilities. These two only allow for one writer process at a time. This one has no multi-process writing available. Redis needs a broker process, which we would like to avoid. Berkeley has a copyleft license, so we were left with LMDB, which actually serves our needs. It has a non-copyleft license. It's an active project with in-memory storage, multiprocess, multithread, and the C++ API. So, done with the storage. For the serialization part, we also evaluated many different frameworks, and the one that stands out is MessagePack, because it has cross-language compatibility, which is the first column, with also the scheme evolution that defines whether it's resilient to new items or items that are missing. It also serves the purpose. It has binary encoding and doesn't require the schema previously to, for example, deserialize a packet that is received. Done with the serialization. And for the compression, we basically want to compress message packets, because it's the serialization is done by message pack. So what we are going to compress is message packs messages, and their motto is that message pack is like JSON but fast and small. It's their motto. And we can actually look at the packets like JSON packets, okay? Because we don't need a scheme. We have the name of the attributes there. We have the values of the attributes there. And this is an example of a packet that we would like to send to the network. We know that we can't make any assumptions regarding the values because they can be of any value. There's an infinite number of possible values that will go there, but the name of the attributes will go there every single time. So what we can do is we can take one packet as an example and generate many different packets with random numbers on the values. And this gives us an excellent training set to train a dictionary-based compression framework. So we use the LZ Bench tool. That is an open source project that uses many different frameworks and gets the times and all the benchmarking for different solutions. And we used it using the Kambada system and Kambada packets, actual Kambada message pack serialized packets. And finally, we selected ZSTD as our framework for this purpose. So done with the compression as well. And this is our final architecture for the LTDV version 2. The API doesn't change a lot. We moved from C to C++. When we were using C, we had global functions. Now we have methods of an object in C++. The initialization and the free of resources is done in the constructor and destructor. Simple. And then we also have a put and a get. The difference is that now the keys are not integers, but they are strings, and this allows us to simply start putting things on the RTDV with a new string, so a new item is just a different key. Backwards compatibility. How did we do this on competition? So we are using CMake to build our software, and we can use an option in CMake to make sure that no additional actions are needed in the code itself. So we basically define, it's one defined in C or C++, and we switch in our macro. So there's a set of macros that were defined that would be able to translate the strings or the old integer keys to strings, which are used in the new version. And this wrapper makes sure that we don't need to change our code. Results. We tried it for the first time in Portuguese Open in Coimbra. It ran successfully without any hiccups. We actually never had to revert to the previous version, which was quite good. But we were still using static arrays. So we basically were using RTDV. We enabled the option, and our structures remained the same. So we were still sending too much data. Then on Nagoya, we moved to dynamic arrays, and again the solution proved to be effective. And because I know you are eager to know the results of timings, because this complexity comes with a cost. For example, if you want to put an item on the RTDV, there are now 3 steps. You need to serialize, then you append the lifetime because it's an internal variable of the items, and then you actually insert the data in the LMDB framework. And when we were using RTDV1, it was below 1 microsecond because it was just a mem copy, and we already knew the size, we knew everything, it's just mem copy. Now it takes a little bit more time, and you can actually see which item is the biggest one in our case, which is the vision info item. The get operation takes a little bit more time. We have to retrieve the data from the LNDB. We need to extract the lifetime because it was not there previously. And we deserialize the data using message pack. And it also takes a lot more time in vision info because it's a bigger... We might need to change some things that we do on the agent because we are passing information from vision to the agent and doing some things on the agent that maybe we should do on the vision, and then just don't share so much information to the agent. About compression, this was not available on RTDB1, so we didn't have any time. You can see in green the batch row data size in this graph. If we serialize it, it becomes the red line, so it triples the size. But then we compress it using STD, and it becomes actually lower than the initial one. It takes 45 microseconds average to compress and 13 average to decompress. So what are the conclusions? This was a success for us. All the requirements that we defined in the beginning were met. It's fast because we think the performance impact is negligible. We're still way below 1 millisecond. It's stable. We used in 2 competitions that we participated last year, or this year actually. Some sweet extras that came with our choices is that now the data can be non-volatile. Previously with the shared memory, when you reboot the computer you lose that information. Right now, because the database is stored in a memory mapped file, you can reboot and recover right where you left. There's cross-language compatibility, so you can develop tools in Android, iPhone, other applications. Data safety, because you are compressing with a dictionary. If there's some other team that is listening to your multicast address, if it doesn't have the dictionary, it can't make sense of the data that you're sending. And you also can define periodicity and phase for your items, so you don't have to share the shared items all periods. And some tools. So there's a dictionary generator that actually took advantage of the cross-language compatibility. This is done in Python. The generation of the dictionary that we use in compression, and a real-time database inspector. This tool runs on the console, and you can inspect all the items that are currently on the RTDB. You can even click enter to take a snapshot of that item and have a look at all the attributes and the values that are there. So what are the next steps? We want to release it open source, just like we did with the previous version with RTDB1. We want to integrate the process synchronization into it, so that you can wake the next process on the pipeline when a particular put operation is performed, and also integrate our logging with this serialized data, because serialized data scales better. We don't know what tools we will be using in the future. And this concludes my presentation. Thank you.
So thank you, Ricardo. Very interesting presentation. Must be any, have to be any questions? Have to be questions? Yeah, there is one.
You showed us data about processes communicating using backbone in a shared file. And when we do that also by file, what happens there?
So basically these times that you saw, that I showed in these times, you are referring to these ones, right? So this is a local operation. You put items or you get items. Those are the times for the local operations. Then there's the COM process that runs asynchronously, that periodically gets the shared items of this agent and then broadcasts it to the network. So that's just the time of a get operation plus the transmission over the Wi-Fi.
Yeah, but because you compressed the data more than before, do you have any measurements on that?
Yes, actually, those are, you have to basically sum the get operation for the item with the compression time, which is the average of 45 microseconds. So the worst case would be more or less 200 microseconds for our biggest structure.
So question, I just saw the graph that it was only the get function. Do I read this correctly that you do the serialization every time you do the get function? Why not do the deserialization and storing?
You have to actually serial so you have your structure that you want to store. If you want to store it here, you need to serialize it. But then when you want to use it, you want to use the data, so you have to get back to the structure, to the raw structure. So you need to come here and deserialize the data to get back what you had initially.
There's no other way to do this and store the deserialized data.
If you store deserialized data, then you come back to the previous version. Basically, you can't store dynamic arrays, for example, or you need to do it particularly for every single class. This is you just say, okay, I want to store this class. You put it there, and it just works like Bill Gates.
So this is an object. The serialized data is an object. It's not a process. It looks like it's a function, but it's not.
Yeah, sorry, I'm from electronics, so this can be very bad design. But yes, this is the process of serializing.
The arrow signifies the serialization.
Exactly.
Okay. There was the first point over there. It was already answered.
So when will it exactly be released and under what license?
You could, well, I can't answer that, either of the questions, but I can give you an estimate. I think we can release it in a month or something like that. Because it's just a matter of getting out of our source code and isolating it. No.
And which license?
I can't answer that. I don't know. But you probably could be able to use it without releasing your source code, I guess. But we still didn't decide on that.
We are waiting.
Okay.
Any other questions, remarks for the Kambada team? No more questions? Well, then we thank Ricardo again. Well, and then for the last time today, we'll have a short break in the room here. You want to present from your laptop? Safer. Do you have a VGA connection? If you want, we can test it. Yeah? Yeah, we can have you sticky. You can just put it in the room. I don't think we have
No, it's not static, it's
yeah, also the beam, like the thing they put around the beamer here is but we can quickly test it, and otherwise somebody has to run it the other side. And is it okay if we put it afterwards on the Wikipedia? Yeah? Okay, very nice. Oh, there's probably means there are lots of figures and videos.
If you want to publish, maybe it's better to publish.
Okay, yeah.
It makes sense to publish.
No, yeah, we only publish.
Make sure that we don't
I cannot play it from the USB. Let's see if that one works. Otherwise, you can. Ask someone.
Nee. Oké, dankjewel.
If you want, I also have the HDMI to VGA. I found someone with. Okay, then maybe it's maybe before we do. Then let's do it. Hier is dat zo. Yeah, so this one does play.
Now we only have to.
I think it's page up, page down.
Yes. Maybe we
What it's converting? So let me see. Do I actually have that? Because I think the video is
the link to the video.
We don't know what.
You don't know what, yes, exactly. So this one, we have a problem.
So actually for your talk I reserved quite some time because I think there will also be quite some discussion.
Yeah, I will
so
some parts of it, but quite fast so that we can...
Yeah, indeed. So don't feel obliged, I would say, to fill the. Maybe I should have already said that before, but don't feel obliged to fill the whole time.
In fact, you don't have the latest Acho que ele está a gravar o terceiro. Você já está a sentir. Acho que ele também está convertido. Mas eu minimizei e agora não está. Eu não consigo. Se minimizo, acho que não consigo.
Qual? Tem notificações não gravadas?
Tem. Acho que não tem muito difícil. Aliás, eu até já gravei o iPad e deve só
Quer apresentar o seu?
Queria apresentar o meu. Há uma coisa aqui que não vai se apresentar deste.
Is it done converting?
Yes, finally. Can we check it from this one? If possible, I will convert it.
There's the VGA is over there.
Tem HDMI? Faz uma coisa do teu.
Sem HDMI? Sim, HDMI.
Mini display port.
No, mini display port. Anything. This is really anything. Nice.
Yeah, most of the computers now have mini display port, or now they have USB 3 type C.
And it's true. Nice. Good that works.
Blocked content whenever you kill.
This? Foi sem ela.
Era USB, but qualquer.
Let's see, so I also have the clicker if you want to use it. Okay.
Sim, acho que sim.
Nee, je hebt zelf toch ook nog een bankje staan. Kijk.
Hey, sure, hallo. Hallo.
This is for you, that's for the name. Yeah.
So, is everybody ready again for the last part of today? So for this, of course, for the whole workshop, we had this idea of this common simulator. And of course, within RoboCup, as you all know, we have different leagues. So our league is just a small part of the entire picture that RoboCup has. And one of the leagues is also the simulation league. I think there are both the 2D and the 3D simulation league. And when we were talking about this common simulator, of course, then you think about the link we can make there to the simulation league. And actually, that's when we thought about some people who we might ask to also tell us something about their experience in the simulation league. Well, that's actually when we came up with the idea to invite auxiliary professor Nuno Lau. I used to be working about 2.5 years, I think it was, in the YETA group from the University of Aveiro. You all know the beautiful building they have. If you visited 2 years ago in the workshop in Aveiro, they have a very beautiful stadium there actually for the MSL robots. But there is also another team, and Nuno Lau is part of that, so FC Portugal. You'll probably tell something about that yourself. Yeah, so this is the ideal combination for us. If we want to work on this common simulator, then having someone from the simulation league telling about how they actually perform games in their league. Well, that's really interesting. So we're really looking forward to your presentation. So I think the best is to use this mic. The microphone. There you go. And the point. Yeah. Stage is yours.
Thanks, Walter, for your presentation, and also thank you very much for the organizers for this invitation. It is a great pleasure and honor for me to be here and try to give you some contribution on what we do in the Simulation League and also what we do with other projects that we have and that are using several kinds of simulators. And so I'm Nuno Lau. I work at the University of Aveiro and also at YETA, which is our research institute. And I will start by a brief presentation. Some of you already know Aveiro, but I'm sure that not everybody knows Aveiro, and so we will talk a bit about Aveiro and the University of Aveiro and our group. And then we will go on with general thoughts on simulation, and then I will report some of the experience and describe some of the simulators we have been using, and also some of the research that we have been performing on the simulator. And I will go back and forth between simulators and some of the work that we have been doing on these simulators. Not all the work that I will be presenting here is very recent, because we are not currently involved with every simulator that I will be describing. So I will be describing the most important work that we developed for each kind of simulator. But the simulators I will be talking about are the soccer server for 2D simulation. Then a spin-off of soccer server, we may say, is CiberRato, because its code is completely independent, but the architecture is in fact it's the same. And we will see an example of how it's developed and how it works. And then we will talk about SimSpark, which is the simulator that supports the 3D Simulation League in two different flavors. The first one with the spheres model, and then we will switch to the current model, which involves the use of a humanoid robot or humanoid robots. We will also talk about UserSim, which is a different simulator that was initially developed for Virtual Rescue, RoboCup Virtual Rescue competition, but that we use for a very different purpose, and we will also talk a bit about that. And finally, we will talk about Gazebo, which is the final simulator that one of the latest simulators that we have been using, and we have been using both for the Europe project and for Cambada, and then we will have the conclusion. So to start, we are coming from Portugal, and Aveiro is the red spot you see on that map. It is about 60 kilometers south of Oporto, and Walter said it is quite beautiful, and I should agree. In the University of Aveiro, it's a quite new university. It was founded in 1973. It has about 13,000 students, 13 research units with a quite good evaluation from our National Foundation for Research. And it has a broad scope of domains that go from science and engineering to communication and art, social science, health, humanities and education. And in our research unit, which is the Institute of Electronics Informatics Engineering of Aveiro, we have it structured in three groups, which are the biomedical, informatics and technologies, the information systems and processing, and then the group that I currently coordinate, which is the intelligent robotics and systems group. And then we have what we call the thematic track, which is called Intelligent Systems for Human Assistance, and that is coordinated by Bernardo Cunha, which some of you may well know very well. Within our group is called Intelligent Robotics and Systems. We call it IRIS, and the mission is to develop integrated architectures and subsystems for intelligent robotic systems, building on synergies between the basic research areas of IETA. It includes overall 23 PhD researchers, but if we go to the full-time equivalent, so if we consider the amount of time each people dedicates to research, for example, teachers only dedicate 50% of their time to research, then we go to a number of around 7. We currently have 9 PhD students, and we had 8 PhDs finish it in the last 2 years. And some of you might recognize the place of the workshop in Aveiro, where we have an open space and then we have a stadium, and I hope that you liked it. For research areas, one of our main research areas is educational robotics, so we use it for several kinds of educational purpose in order to teach technology and to have a purpose when you build technology. We also have a research area on anthropocentric robotics that includes, for example, the Intel Wheels project that we will be talking about. We have another research area on autonomous driving that is, I'm not very focused on it, but other people from the lab are working on it. And of course, you all know that we work on multi-robot systems with Cambada project, of course, but also with FC Porto and other projects. Our timeline and research topics, you can see that from educational platforms, mechatronics, navigation, human-robot interaction, artificial vision, learning, etc., over the years, we encompassed many different topics. We also have a quite good record on projects that we have been working on. And the WEE that you see on the top are years in which we have been either world champions or European champions in RoboCut. And now for some thoughts on simulation. We can define simulation as the imitation of some real state of affairs or process over time, representing the characteristics that you want to take from that environment, or that you want to study from that environment. We can study to model natural systems, to do some performance optimization on some process, or also to help you in decision making, because by using a simulator you can do a kind of what-if analysis and then get a better decision based on the results that you get from a simulation. It is mostly applied to complex systems that are impossible to solve mathematically, because if you can solve the problem analytically, then it's better to solve it analytically and you can skip simulation. There are various examples of applications of simulation, and we can talk about wargaming, flight simulators, transportation systems, aerodynamics, robotics, and of course games and sports. And we can say that simulation is not appropriate if the problem can be solved by common sense, or simple calculations, or analytical methods, or direct experiments. You should also consider costs, of course, because sometimes you will not save any money or human resources if you use simulation. And in order to do simulation, you also need data. So you need some data in order to feed your simulator and then to work with it. And you should always also consider simulation when you will be able to capture the key features of your system in the simulator. And it's very important to keep the simulator at the adequate level of abstraction. Otherwise, you can have a simulator that is either too slow or too imprecise, and it will not give you any results that you can use for your study. And so, when mathematical analysis methods are not available, you can use simulation. When mathematical analysis are available, you can use simulation, and it provides you practical feedback. You have higher control, lower costs, and you can do sensitivity analysis, training tool, and without disturbing the real system. If you consider the case of robotics, then you have a lot of advantages by using simulators. In fact, it is much less expensive than using real robots. It will ease the development and testing of new models of robots, so you can test different models without having to actually building them. You can test new algorithms much faster in general, so you have less development and testing time. The problem can also be studied at different levels of abstractions, and it's possible to test different components. And one of the most important things for us that are working on multi-robot systems is that you can, in fact, use it to test multi-agent coordination methods, and in fact this is one of the main assets for having a common simulator within the league. All tests can be, of course, performed without damaging the real robots. You can repeat tests very easily, because, for example, to set up the initial conditions, you don't have to do any physical effort. You just have to have a good script and a good framework. You can also have very detailed information that is not available in the real world. For example, one of the problems that we have in the MSL is to have a ground truth information. So if you want to test your localization, it is very hard to know where exactly is your robot in order to see if your localization system is providing you good results. But in simulation you can do it very easily, because you can, in general, you have access to the exact position of every robot, or if you want, you can also get center of mass or center of pressure or zero moment point or anything like that. So it's also very important that we have quite good simulators today, and so we can use these simulators in order to test things, and then with little changes you can change and apply your techniques in real robots. Now to go to the experience and research on different simulators. To start first about simulation 2D, we all know about RoboCut and about RoboCut Moto. And about RoboCup leagues, so we have simulation, small size, middle size, standard platforms, and rescue. We also have simulation and then virtual rescue and robotic rescue, junior at home, etc. But in simulation 2D, what we use is the soccer server. The robots are virtual, the environment is 2D, of course. The dimensions of the field are quite similar to the real ones. And then agents are controlled by different processes, and simulator sends and receives messages receives actions from agents. Teams work with 11 agents against 11 agents plus a coach. And how does the simulator work? In fact, the simulator works as a client-server system in which the simulator is the server and the clients are the agents. The agents perform as the player brains and connect through UDP sockets to the simulator, and then the server receives agent commands, simulates the movement of objects, and sends the perceptions to the agents. One important thing here is that all agents have exactly the same capabilities. So, and the interface that is provided by the simulator is the same for every agent. Agents take all decisions during the game. There is no human determination. But in the simulator, you have quite high-level commands and no physical engine. And so the simulation characteristics is real-time. It is very distributed with 84 processes. And in a competition setup, you have many computers supporting the competition. So in each computer, you do not run more than 3 agents, for example. And you have a different computer for the simulator. The state is inaccessible because, as we will see, you don't have any vision sensor that will provide you with complete information about everything. You also have limited resources because the simulator is simulating what happens with a human, and so if an agent runs for too much time, what will happen is that it will get tired, and so it will not be able to run at the same speed. It will have to come back to a lower speed, and it is a multi-objective cooperative and diverse environment. So the field is like this. You can see some posts that are around the field in order to localize. You have an automatic referee, you have an online coach that can perform instructions when the game is stopped, and you also have a human referee for complex situations. But the model is very, very abstract. For example, a player can kick the ball if the ball is within a certain distance. And when the ball is within that distance, you can kick the ball in any direction. So the ball can be behind of you, and you can kick the ball forward, which would be quite hard for a physical implementation to do. The visual perception is limited, as we will see in the next slide, and the oral perception is also limited, so only one player can speak at a time, or can be heard at a time, or more. And so, in terms of vision, for example, there is a certain vision is limited in the field of view, and then there is a certain distance in which you see everything. After a certain distance, you start losing the vision of who is that player. You don't see the numbers. After another distance, you don't see there is a player, but you don't know which team is it. And after that distance, you don't even see the players at all. And the agents that you can do are, for example, the turn, the dash, the kick. Turn is for rotating, dash is to accelerate in a given direction. Kick is to kick the ball, and catch is used by the goalkeeper in order to catch it. You also can turn neck and change view in order to control your sensors. And then for communication, you can use the say. You can also have tackle and things like that. So DFC Portugal, what is the point here? This was a project that was started in 1999, and our point was to develop research in intelligent robotics and multi-agent systems, and then, as I told you in the beginning, as fast as possible, to convey the technologies that will develop in simulation to the real robots. It is a cooperation project between the University of Aveiro, the University of Porto, and the University of Minho in Portugal, and we have used it for several different domains. The main point is the coordination of agent teams in adversarial environments. One of our points was to develop a strategic model. So how can you model the strategy that you will use for soccer game. That is one of the things that we focused on in the beginning, and we think we achieved a quite good model. Then we have the level decision, optimization learning, development monitoring tools, communication, and the level architecture. For example, for low level skills, you have a ball that is traveling over the field, and you should know where exactly is the first point that you will be able to catch it. And so you have to have a model of the agent and a model of the ball movement, and considering the noise that you have in each actuator and perceptor, you should be able to catch it. One of the innovations that we introduced this year was an optimization kick, because the problem of kicking the ball or accelerating the ball in a given direction is not easy, because in order to have the ball well accelerated, you should not only perform one kick, but you should perform several kicks in succession while the ball is inside your kickable margin. And so, in order to know which kicks and at which positions, we apply an optimization technique, in fact an online optimization technique, and the results were quite good. As I told you, we try to develop a strategy, and this strategy should be on one point very good for simulation, but also be able to be applied in several different leagues. And in fact, we used it for FC Portugal, but then we adapted it for Cambada, for Portuguese team, which is a team that competed in the Standard Platform League, and also for 5TPO, which is a team that also already competed in a small size league and middle size league. It in general participates in the Portuguese Open, for example, and it also uses a kind of strategy that is derived from strategy developed originally by FC Portugal. The common framework includes strategic coordination. For formations, we use situation-based strategic positioning. We have dynamic position and role exchange in order to always have the best robot for each role. And then also, we have already heard about set plays today from different teams, and we will hear again about set plays and how we manage set plays in FC Portugal. We also have a generic optimizer of skills decisions, because this is very important in robotics in general, and in simulation it's even more important, and bridging the gap. So the formalization of a team strategy is like this. So we can define a set of tactics. Tactics are things like 4-3-3 or 4-4-2 here, and then for each static you can define several different situations, and then for each situation you define a formation that can be more advanced or more close, etc. And for each formation you define player types, and you can assign different player types to each player, and these player types have three different models, which are the strategic behavior, the ball possession behavior, and the ball recovery behavior. So for ball recovery, you can configure, for example, the tendency of a player to be more positional in its way of defending, or to mark a pass line, or to mark a player. In ball possession, you can define if you want to have a game that is more on short passes, or long passes, or shots, or etc. So in order to coordinate a team of soccer, it's very simple. You have to score goals, and you should not suffer any goal. So soccer is quite simple, as Italy knows in the last few days. And for coordination challenges, we have role assignment, formation control, plan execution, and communication. Formations are quite important, and because they should provide you with a dynamic way of positioning your team over the field. Most teams, and also this applies in the middle size, we use role based models, but if you look in the literature, you can find the strategic positioning with attraction and repulsion by Stone, and the locker room agreement, and then the model we developed, which is called situation-based strategic positioning, in which we have distinction between active and passive situations, and different movements for different situations. And then we also applied it to Akiyama, or we combined it with the Akiyama effort in 2007, and we have SVSPDT. In strategic positioning, for different situations, you have different formations over the field, and we can do it for active situations. You do active behavior with ball.
for passive situations, you do what we call strategic positioning. Here you can see that, for example, the FC Portugal team, which is the blue one, is very well positioned in the field, while the team from CMU and ATT is, it seems that a lot of players are just following the ball. For dynamic positioning and role exchange, what will happen is that you always consider which is the best roles for every player. And for example, here, what will happen, so you should focus on what will happen with player 2 and player 9. And I need to very quick. Okay. So you see that player 9 passes the ball to player 2, then again to player 9, but player 9 went to the border, and so player 2 assumed the role of player 9, and he went to the central part of the field, and that was quite nice because it wouldn't be good to have two players on the sideline. And so we do it dynamically, of course, this was all decided. And so we started the project in 1999, and we came to Amsterdam for our first competition, which was called the Euro Cup, and we were 2D champions. Then we went to Melbourne for the main Robo Cup, and we also were champions there. In Robo Cup German 2001 we were also champions, and in Seattle we were coach competition champions, and we had the third place. Afterwards, as I told you, we combined this with the work of Akiana. And so what happens here is that in order to have more complex formations, what we do is we define several positions in the field, and for each position you can define which is the formation that we want. And then when you move along the field, you do an interpolation between the three vertices of the triangle that result from the line triangulation, and you can have different formations. And for example, here you can see how the formations are defined. So in order to define a given formation, you have to set which are the points that you will consider. If you want to have a symmetric formation, every time you define a point on one side, you get to a point on the other side. And as you can see, as you move the ball around, now the formation does not move. But if you fix to the upper right corner, if you move the ball, if you move the players to the position where you want them, and then you set that point as the new formation, now the formation moves smoothly as you move the ball around. Okay, so this is what we want. If you go to the initial triangle, it doesn't move because we didn't change any of the formations within those three triangles. You can of course save the formation, but you can also get it. And for example, this is a formation that we can use for middle size. This is quite a defensive formation. But if you want to have a more attacking formation, you can keep one of the players in attack, and then you can, as the model moves around, you also keep a player in attack in order to receive a pass, and he should always be in a good position in order to receive a pass. If you want to fine-tune your formation, what you'll have to do is to define more points in triangles and do it. So as I told you, when we came back in 2000 from the Amsterdam competition, we thought, well, we have a competition in Aveiro, which is the Microrato contest, which first edition was in 1995. And the point here is, you have real robots, they are placed in a home area, and they have to find where is the target area. And in the target area, there is a beacon that emits infrared lights. And we thought, well, using the architecture of the soccer server, we could easily build a simulator that would allow to have a simulation competition similar to Microrato. And what we did was in fact that. So the CyberCab simulator was developed in Aveiro, but its architecture derives directly from the soccer server. So we have a simulator, the agents connect to simulator using UDP sockets, we have a visualizer that is an independent application, and then we can save the logs of the competition as they work, and we have several files that define the labyrinth, the grid, and the parameters. The simulator agent interaction is exactly as the soccer server, so the simulator sends a perception, the agent reads the perception, takes decisions, sends actions, and then the simulator moves the robots and it loops around. Time is discrete here. For visualization, we have several kinds of visualizers. The one you are seeing one of the options, and I would like to show you what we have here is in fact the serial card simulator in the top. What the robot wants is to find the 3 cheeses right now, but he cannot see the cheese through the green walls. So he has to look around, and what you are seeing below is what he already knows, in fact. So this agent is also giving a graphical view of so now we found the second cheese and he went there, and now he's exploring again, and he will go back to where he was. If we go now to the SimSpark and to 3D simulation, what we did here, so first about the 3D simulation, why did the simulation lead consider a 3D simulator? As you can see, the 2D simulator is quite good to work on multi-agent systems, but it's not so good for robotics, I would say, because the level of a dash or the level of a turn is very, very different, or the things that you can do with a kick effector are very, very different from what you can do with a real robot. And so it was envisaged by the simulation 3D community to have a simulator that would work on 3D, that would be based on physics, on real physics, and or simulated physics, but quite similar to real physics, and that would allow us to go closer to a real robots. And so it started in 2004, and then it moved to humanoid models in 2007, and then to now in 2008. It has a strong relation with the SPL, and now it works with games of 11 against 11. And it is quite difficult to create skills by hand. It is based on SimSpark simulator. This is a simulator that works on 3D, but it's a generic simulator. So it is currently mostly used by the 3D simulation RoboCup 3D simulation lead. But as you see, it was already used with quite different models, and it can be used with other different models. New simulations can be developed using a sim description language. The physical engine is based on Open Dynamics engine. It includes a multi-threaded execution that allows it to be quite fast, in fact. And the main constants are the server, monitor, and log player. Server is simulator, monitor is the visualizer, and log player allows you to repeat. It has some general perceptors and effectors that include several joints to build new kinds of robots. And so you have the physical engine, then you have the sidecast, which is used for object management. You have the simulation engine, and in the beginning you also had the Spades middleware that was used in order to take into account the network effects and also the thinking time of each agent. We quickly took that out because although it worked well, it was very, very hard to use and to configure, and it gave lots of problems in that respect. And so now we are not using it anymore. In terms of the interface between the simulator and the agent, it's quite similar to the 2D simulator. So, for example, for vision, we don't get any image. We get a message that tells us that flag with that ID is at that coordinate in 3D. The goal with that ID is at that coordinates in 3D. And the team name, a player with that team name is those coordinates, and about game state. You also get images that give you an abstracted way of vision. For actions, in the sphere model, what you could do is a drive, which would add a force in a given direction to the robot, a kick with a given angle and force that applies a radial force to ball, and then all controls the vertical direction. So you could not kick the ball in any direction anymore. Now you could only kick it radially, which involves much more planning in order to know where you are going to kick it. You also had a pin effector in order to position your agent in the beginning. And what we did here is that we defined a flux that, when applied over the field, tells you, gives you a a continuous function over the field that will tell the robot where do you want our game to pass. So if you have a high gradient of the field in the left side of the field, that means that you want your game to go through there. If you have it on the middle, that means that you want your game to go through there, and so you can configure if you want to play through the L's or through the center or through different parts of the field. And then, in order to decide what you will do next, we basically take into account three things, which are the flux, that is some kind of positional gain that you get if you pass the ball to a given position. The positional gain is determined by getting the difference between the place where you want your target to be and the place where you are. The safety means which are the chances that for example the ball will go out of the limits of the field, and also the easiness which applies for if the opponent will catch the ball before you, or how much time do you have to take in order to do that kind of thing. And what happened here, so still using the spheres model, was that it took us through 2 years to work this out. So in 2004 and 2005 our results were not so good, but as you can see in 2006 you already see some techniques that derive from real soccer. So the FC Portugal team is the blue one, then you have the red team, which is from Germany, if I'm not mistaken, and we have just seen a goal, but you can see this is a corner, and then you missed the goal, but it was quite close. And so we also had quite good results here. Again, in the Netherlands, we came to Eindhoven in 2006, and we were 3D simulation champions and 2D second place in the 2D. And in RoboCup 2006, we were 3D simulation champions again. And then we were in the technical committee of the simulation league, and although we had been champions, we decided to change to the humanoid model and to restart everything again. And because, of course, the code in order to control a humanoid robot is very different from the code that you have to do in order to control a sphere robot. For the current version of the 3D simulation, what we are using is a 3D simulated agent that is very similar to the Now robot, and that includes 22 degrees of freedom. It is about 57 centimeters height and 4.5 kilograms. It includes a gyroscope, 4 sensors, and you can control every joint, of course. And you can see here a little of how a game works. This is us against Magma Offenburg. Magma Offenburg are a German team that is currently the second place in Japan. Well, they took the second place in Japan. We have been most of the times the third place in this league, but this year it was quite bad and we went further down. But you can see that they already are passing. For example, this was a pass, but they still have problems in moving around, and especially in kicking the ball. Now you will kick the ball, but you will take quite a long time in order to kick it, and it almost gave time for the opponent to get the ball again. And so you have visual information, as we saw. Here you can hear what the other says. You can control joint angles. You have the solarmeter, gyroscope, and for resistance at field. You control the joint velocity for each joint. You can have a say command in order to convey information to others. You have a beam command in order to position your agent in the beginning, and the init and create are also used in the beginning. The FCPO humanoid agent is built around several models, like the skill model, the logger model, the utils model, optimization strategy, physics, world state, and geometry. And for example, one of the points that the simulation allows you to do in a very good way, and it's better than real robots, is to use optimization in order to derive your skills. And so, in generic optimization, you want to find the best configuration of a set of parameters to achieve a goal. And what you want is to maximize or minimize the quantity, that is called the objective function, and the independent variables are called decision variables. Decision variables may have variable domains that restrict the amount of things that you can do, and they can also have several other constraints that you should also consider. And so what we did here is, in order to have a good optimizations, we should exploit parallelism, okay? And so what we did is that we have an optimization server that links to the simulator and that can spawn several executions of the current parameters or the set of parameters that you want to test in different computers or in different cores within the same computer. And by using this kind of optimization, we can optimize it much faster than what we could do otherwise. Here you have what happens with a 4-phase forward walk using hill climbing technique, hill climbing optimization technique. And in the beginning you have a robot that walks like this. But if you use genetic algorithms, you were able to have a robot that walks a little bit faster. And if you use genetic algorithms with a different model, you can even make it faster. It's the model is different, so it was able to. One of the things that we focused on more recently is also on black box optimization, but by using techniques that also use theoretical information theory in order to get the best optimization. So we want to search our distribution space to find the distribution that maximizes the computation of the rewards. And so what happens is that you have a Gaussian policy initially in order to sample the environment, and you get those samples and you evaluate them. And what you want to achieve is, now what can I get from these samples in order to say how should I sample next. So you evaluate your samples and you see that that one is quite bad, that one is much better. And what is this telling you? This is telling you clearly that in order to get your next evaluation, next sample policy, you should move to your right? And so by using this information, we move it to the right and then we sample it again, and we can get new values that were probably better than the previous ones. And so we are using this in order to maximize the expected return, but we are bounding the expected information loss using the KL divergence. We are bounding the entropy loss also in order to not have overfitting or converge to a point that is not the maximum yet. And we get a new distribution like this, and then we have a compatible function approximation. And what we did here was also to make the optimizations able to work on contextual frameworks. So what do we mean by contextual frameworks? A contextual framework is a framework where we do optimizations for several different contexts. For example, if you want to optimize the kicking behavior, in general you optimize it either to have the furthest length possible or to have a given predefined length. But what we want with the different contexts is to optimize the kick behavior, but to be able to optimize it, for example, for different contexts where each context is a different distance. And you can do it by optimizing for a kick for 3 meters and having a different optimization for a kick for 5 meters. But we want to do the optimization for 3 meters and for 5 meters within a single run of the optimization. Because we think that the information that we got for 3 meters is also important for or maybe important to optimize the 5 meter optimization. And also by using this you can get a kick that in fact may be used for any distance. And what you used it in a simulation league challenge that happened in 2015. And here the point is the robot will be placed at different distance. Now, for example, it is at around 3 meters of the center of the field. And what we want is to kick the ball so that it stops by the center of the field. And then the robot will be placed at 4 meters and we will have to kick it again. And then the ball will be placed at 5 meters and we want to kick it again. And so what we got by using this kind of optimization in which we optimize everything in a single step was something like this, in which at 3 meters it will kick the ball and it is quite, the ball stops quite close to the center, and then you have 4 meters, and over the 10 kicks that we got an average distance to the center that was 28 centimeters, which I think is quite good. So even for kicks that are very far, as the 12 meters kick, we can get through optimization, so this was not encoded at all, we can get through optimization a distance to the center that is very, very close. So we also have a set play framework, but I think I'm going to skip it because I think we already... What happens here is that we developed it for 2D simulation, but it was first applied in 3D, in fact. Then it was also applied in 2D, and we had the first instantiation of this framework for the middle size a few years ago, but then it was in a moment where Cambado was changing the structure of its code, and we could not apply it because we would have to re-adapt it again. And now we have Matthijs from Tech United that is doing a very good job in Aveiro, and that is working on adapting this simulation, this set play engine to the middle size league. And in fact, it can already run set plays with real robots, and it works quite well. And so we also have a graphical tool in order to define the set plays. We have a formal definition of a set play that is using a language that was previously defined, and then we can test it and we can repeat it. Just for a quick overview of how it works. This is how you define a new set play. You define if it's offensive or defensive. You define the initial situation, and then you define the participants that you want to involve in that set play. And each set play is constituted by several steps. And then you can just say if you want player 7 to pass to player 5, you just set a pass, and then this will run forward, and then we can continue describing the set play. These are some of the results of the SC Portugal over the years, so we have quite a good record of results from. And now I would like to talk a little bit about user scene. User scene is a unified system for automation and robot simulation. It was first developed to be used by the RoboCup Virtual Rescue system, but now they changed to Gazebo. So I would not advise you to consider this as a good base for the common simulator, as the maintenance and the community is quite low at the moment. It has good visualizations but not so precise physics, and this also comes because it is based on the Unreal Tournament game engine. And so for games, as you know, it is much more important to have a good visualization than for the physics to be completely very precise. But one of the things that it already has, for example, is a model of an omnidirectional camera that is very, very similar to the ones that are used in the middle-sized league. What did we use this for? We use it within a project that is called the Intel Wheels project, in which purpose is to develop an intelligent wheelchair, okay? A real intelligent wheelchair. Why did we need a simulator if we want to build a real intelligent wheelchair? We had a simulator because we want to apply it for people with cerebral palsy. And people with cerebral palsy each person has a distinct kind of capabilities. Some of them can control their hands, some of them can control their head, some of them can talk, some of them cannot talk. And so we would like to have an interface that is adapted to each person that will really use the wheelchair. And then in order to get which are the capabilities of each person, we use the simulator. This is the general system architecture. So we have a data analysis system that will in the end provide a common language advisor that will tell you, well, this person should use voice and joystick, for example, while this person should use add movements and voice or something like that. Then we have a multi-model interface, a control model. Here we can have the simulated or the real intelligent wheelchair, and we develop an Intel Wheel serious game in order to get information on capabilities of the person. And what happens is that, so using the user sim, we develop an environment that is quite similar to the place where the cerebral palsy patients are. We included a model of a real wheelchair that is in the simulator. And then we developed a serious game in which by controlling the wheelchair, either with the air movements or voice commands or joystick or different capabilities, they would have to pick these blue balls that were around in the environment. And in the end, what we got is something like this, where so here you have real patients with cerebral palsy that are using the virtual intelligent wheelchair by using simulator. The first one is controlling the movements with air movements. The second one is controlling the movements with the voice commands, and the last one is controlling the movements with a joystick. And so by analyzing the data that we got from here, we can give each patient the best interface that is adapted for his capabilities. Finally, I would like to talk about Gazebo. So Gazebo is a general robotic simulator. It has a robust physics, and several physics engines are available, like ODE, Bullet, and others. Some of them are already prepared in order to be GPU accelerated, which is also a nice extension. It has high quality groups and very good ROS integration, and it is widely used, and it has a large community of developers. And in fact, you can already see the roadmap for the next 3 or 4 years if you look into the Gazebo site. The main concepts are worlds, which define the environment, in fact, models, which define specific things that you can place in the environment, meshes, which define how your object will look in the graphical window, and plugins that allow you to develop different robots, different controllers, different sensors. And communication is made through publish subscribe. So this is a general view of the Gazebo simulator, where you have the world, the model, you can have joint models, body models, or sensor models, and then you have clients that communicate to controllers and that provide data and comments. Where did we use it? We used it within the European project called European Robotics Challenge, where we are participating in a consortium with an Italian company called IMA, which world leader in building packaging machines for tea and for coffee and for several other things. So the European Real Robotics Challenges is divided in 3 challenges. We are participating in challenge number 2 for shop floor logistics and manipulation. And then in stage 1 is based in simulation with all candidate teams. Stage 2, a selection of 5 teams per challenge. And then in stage 3, which is the current one, and it will end in May 2018, a selection of 2 teams per challenge. And the University of Aveiro, together with DIMA, reached stage 3. And see, this is part of what we made in stage 1, and then this is part of what we made in stage 3. So what you can see here are blanks that are then used by the packaging machine in order to make boxes, and we have to fill the packaging machine with them. But in stage 1, we used the Gazebo simulator. In fact, the Gazebo simulator was provided to us, so we didn't have to change anything. It was the same for every team, in fact. And what we had to do was several pick and place operations, like for example, assembling a puzzle. And so the first robot had to plan how would it pick the parts and how to place them in the green area. Now it is placing the smallest cube in the corner. It will pick the next part. It is doing all of these automatically, of course. Now it is adjusting. Sometimes what will happen is that after adjusting, it is not in the right place yet, so it will do it again. And he knows that it was not in the right place, and then he will change to the next part, and he will also put the last one. The last one is a little bit more difficult because it has to fit in the others, but you will see that he also has a good strategy for that. So first he must make it fall down. Then now this is quite difficult because the margin of error is below 1 millimeter, and when it tries to push it, it is not completely okay. But so you will try again, and it doesn't fit yet. So now we will push the green one, and hopefully it will fit. At least it fitted the last time I saw the video. So, for the simulator, the Commander simulator, last but not least, it was developed around 2010, and it is also gazebo based. It provides a single team simulation, so we cannot currently simulate 2 teams with this simulator, but we can